Hi, NA Physics, it's Mr. Neff. Today, let's talk about natural frequency and resonance. But before we do, when the car was out of gas, why couldn't it get into the crowded garage? I'll tell you at the end of the video. On the video with standing waves on strings, I talk about natural frequency. And I thought I could do just a little better job talking about what natural frequency is and what resonance is. And so you'll be able to tie those two ideas together a little bit. On the standing waves on strings video, I show how certain particular special frequencies can cause the string to vibrate with an amplitude that is many, many times bigger than the amplitude of what's driving this. You'll see, or you saw on that video, that this oscillator is going to vibrate certain small amplitude. You can see it here. We have a small amplitude. However, whenever you set it to just the right frequency, the amplitude of the standing wave pattern gets humongous. That happens whenever you're at a certain frequency. That happens whenever you're twice that frequency, when you're 3 times that frequency, 4 times that frequency, and actually all integer multiples of that frequency are going to give you this humongous amplitude standing wave. So now, those frequencies that will cause that humongous amplitude are called natural frequencies. And everything, no matter what it is, because of how it's made, what it's made of, and so forth, have natural frequencies. Say I wanted to figure out what the natural frequencies were of a particular thing. Nothing could be simpler. All you have to do is hit that thing. So I happen to have here 2 cups. They're about the same size, but one is made out of plastic and the other one is made out of paper. And I'm going to take those cups and I'm going to take them off the screen and I'm going to drop one of them for you and then I'll drop the other one. And based on what you hear, I'll bet you'll know which one is which. So here goes the first cup. Ready? Okay. Which cup was that, the paper or the plastic? Rewind it if you have to. And here's the other cup. Ready? Did those two sound differently to you? They sure did to me, and I hope it came across the video. The first one that I dropped was the plastic cup, and the second one was the paper cup. The plastic cup, well, it just sounded like plastic, and the paper one, it sounded like paper. That is, in the frequencies that came to your ear, the information was decoded there about what it was made out of. Right? If I had a cup made out of metal, if I had something that wasn't even a cup, it was a different shape, you'd know the difference just based on what you heard. So if you want a natural frequency, all you have to do is strike the thing. And if you do, you're going to see or hear the natural frequency. So you can see, I say here, that the natural frequency are those frequencies that the object will vibrate when it's hit or struck or strummed or somehow disturbed. Now, natural frequencies are how you can tell a paper cup from a plastic cup, but it's also how you know who someone is on the phone before they even identify themselves. It's also how you know what kind of instrument just played a note. Now, it's possible to take a brass instrument, maybe a trombone, and a stringed instrument, maybe a viola, and play the same note on both of those instruments. Everyone's going to know which one was played on the stringed instrument and which one was played on the brass instrument. How do they know? Well, they know because not just the note is in that sound, but so is harmonic content. That is, other frequencies that tell you, well, something about the origin of that sound. And so each different instrument is going to have certain frequencies that you're going to be able to say, oh, that was that kind of instrument. Now, some instruments are going to play a real pure note, like a tuning fork would play a pure note, just give off one frequency. Whereas other instruments would give off multiple frequencies, and you're going to see something. If you're going to describe the sound as musical, you're going to see that the frequencies in there are going to have a mathematical relationship. Online I found that a tuba is going to play at 200 and 400 and 600, and so you can see a mathematical relationship between these frequencies, and so we would call that musical. Versus if I drop a pencil, or like I just dropped those cups for you, if I do that and I identified what frequencies were present there, there wouldn't be a mathematical relationship between those. So I just call the sound that I heard noise. Now, why is the natural frequency important? Because if you can find it, And if you can make the object vibrate at that natural frequency, then you're going to get those humongous increases in amplitude. And that condition is called resonance. And so resonance is forcing something to vibrate at one of those natural frequencies, and that will cause large increases in amplitude. A couple of classic situations with that is the ability to dribble a basketball. To dribble a basketball, you have to know when to push it down again and again and again. And that's going to vary based on how much air is in there, how thick the walls of the basketball are. What if you had a different kind of ball? You would have a different frequency of oscillation on that. And so the ability to dribble a basketball, it translates physically into an ability to match the natural frequency of the basketball. So is an ability to push a swing. If you want to push a child on a swing and make them go higher and higher and higher, you have to know right when to push. You could push a little too early, you could push a little too late, and be very, very ineffective at making the swing go higher and higher. Versus if you push at just the right frequency, you'll get resonance. You'll get large increases in amplitude, and the swing will go higher and higher and higher. I'll put in the notes a link to a pretty neat video about a disaster that happened in part because of resonance. It's the disaster of the Tacoma Narrows Bridge collapse, and you should check it out. It's a pretty interesting thing. So I hope today's video helped you understand natural frequency and resonance a little bit better. And when the car was out of gas, why couldn't it get into the crowded garage? Not enough vroom.